In this video, I want to give you a more complete look at oxidation and reduction reactions in organic chemistry. I want to focus particularly on how to make carbonyl compounds through these oxidations and reductions. Let's jump right in. So I've laid out for us here some of the simple oxidation and reduction reactions. And in organic chemistry, it's easier to figure out when you have an oxidation and when you have a reduction than it is maybe in general chemistry. Because an oxidation in organic chemistry is making more carbon-oxygen bonds, and a reduction is making fewer carbon-oxygen bonds. So we can see here we have an alcohol. We call this alcohol a primary alcohol because the alcohol carbon has one carbon attached to it, so we call it primary. And if we oxidize this primary alcohol, the first oxidation step is you lose two hydrogen atoms. So we can lose one hydrogen atom, two hydrogen atoms, and we go from one carbon-oxygen bond in this alcohol, and we oxidize it, we make an aldehyde with two carbon-oxygen bonds. So we still have one carbon attached to the carbon with the oxygen. We lost these two hydrogens, so now we have a carbonyl, carbon double bond oxygen between these, and we have a carbon, carbon, and hydrogen still there, an aldehyde. An aldehyde has two carbon-oxygen bonds, and if you further oxidize it, you make three carbon-oxygen bonds. And the place where you insert one more oxygen is between that carbon and that hydrogen. They can open up and take in one more oxygen atom. So instead of two carbon-oxygen bonds, now we have one, two, three carbon-oxygen bonds, and we call that a carboxylic acid. So primary alcohols can be oxidized to aldehydes and can become carboxylic acids. You don't have to memorize that. You can just remove those two hydrogens and make one more carbon-oxygen bond at each step. The opposite reaction is called a reduction. I can go from three carbon-oxygen bonds, add a reducing agent, and reduce it from three carbon-oxygen bonds to two carbon-oxygen bonds. And from two carbon-oxygen bonds in an aldehyde, I can further reduce it to one carbon-oxygen bond in an alcohol. So oxidations are more carbon-oxygen bonds, reductions are fewer carbon-oxygen bonds. So let's say I have a secondary alcohol. That's an alcohol with two carbon atoms attached, a secondary alcohol because of these two carbons. If I add an oxidizing agent, I'll remove these two hydrogens. So I'll have a carbon with the C double bond O, two carbon-oxygen bonds, and these two carbons on it. So you can see how we can just figure out what it'll make. One carbon-oxygen bond to two, remove these two hydrogens, and these carbon atoms are still on that carbon, and we call that a ketone when it's a carbon-carbonyl carbon. So secondary alcohols can be oxidized to ketones, and they can't further be oxidized because there's not this carbon-hydrogen bond to insert one more oxygen, so you're stopped at the ketone. It cannot further oxidize. Ketones, if you add a reducing agent, can go from two carbon-oxygen bonds. You add the two hydrogens across that, and you end up with an alcohol. Carbon, 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 and my C double bond O becomes a C single bond O and makes an alcohol. Tertiary alcohols, if I try to oxidize them and lose two hydrogen atoms, well, there's one, but there's not one on this carbon. So tertiary alcohols cannot be oxidized. I don't have to memorize that. That just makes sense. I can't find a second hydrogen. I would know, oh, I can't do that. And if somebody tried to, they would come up with something that would look like this. Some kind of, oh, I'm going from one carbon-oxygen bond to two, and they would have a carbon that would be too many bonds, so you can't do something crazy like that. All right, now back to this. Now that we understand what oxidations and reductions look like, let's look at some oxidizing agents and reducing agents, those chemicals, and look at some that we've seen in previous videos. For oxidizers, we have strong ones like sodium dichromate, and there's 7 oxygens on there, so that helps me remember it's an oxidizer. Sodium dichromate, Na2Cr2O7 with sulfuric acid. That makes chromic acid. That's a good oxidizing agent. So if I add chromic acid and acid to this alcohol, it would oxidize to this ketone. And similarly, if I added sodium dichromate, an acid, to this alcohol, it would oxidize to the aldehyde, but it's strong, and it wouldn't stop there. It would keep going all the way to the carboxylic acid. I couldn't stop it. That's why we need some weaker ones. Weaker ones can maybe stop halfway. So down here, I could also have oxidized this with PCC, this weak one. And it will also take alcohols to carbonyls. So I could have turned this secondary alcohol into a ketone with PCC or this one, the weak one or the strong one. But up here, here's where it matters. If I use PCC, it oxidizes to the aldehyde and stops there. PCC is not strong enough to take me all the way to the carboxylic acid. So it's good to have the strong one that takes you all the way and the weak one which takes you halfway. So the strong one, sodium dichromate, the weak one, PCC. Let's look at going the other way with strong and weak. Previously in other videos in reductions, we saw that LAH, lithium aluminum hydride, is a strong reducing agent. It's the strong one. And sodium borohydride was our weak one. So if I come up here and let's start here. If I take a ketone and I add LAH to it, lithium aluminum hydride, I can reduce from a carbonyl to the alcohol. And notice there are 4 hydrogens on here, so I'm adding these hydrogens back. I'm reducing it. Or I could have used sodium borohydride, and they could take ketones and reduce them back to an alcohol. Either one, I could have used strong or weak, just like I use strong or weak oxidizers this way. Now for this one, if I use the strong LAH, lithium aluminum hydride, it can reduce to the aldehyde, and it doesn't stop there. It goes all the way to the alcohol. So you might think, well, let's use sodium borohydride for the weak one to stop halfway. But unfortunately, that's not strong enough to reduce this at all. So LAH can also take aldehydes to alcohols if it can take the strong one to alcohols. And or sodium borohydride can also do that, can do that step. The sodium borohydride has no effect on this carboxylic acid. It cannot reduce it. So those are all ways we've looked at previously, but I still need to find a way to do this reduction. How do I go from this carboxylic acid and stop at this aldehyde? So that's what I'm going to teach you in this video. If I have a carboxylic acid and I want to reduce it to an aldehyde, but I don't want it to keep going to the alcohol. That's what I'm going to do now. How do I stop halfway? Well, unfortunately, we don't have any really good ways of doing that with one chemical, one reagent. We have to do it in 2 steps. So here are the 2 different ways you can do that. First, you need to turn this OH into a different kind of group. So one way you can do it is use thionyl-chloride. And we've seen previously that this takes OH groups of alcohols and turns those into chlorides. For a carboxylic acid, it does something similar, and it turns the OH of a carboxylic acid into a good leaving group, a chloride. We call this an acid chloride because it's the chloride that comes from a carboxylic acid, an acid chloride. And then once you have this good leaving group, an acid chloride, we're going to add a hydrogen source, kind of like LAH, but instead of 4 hydrogens, we're going to add 3 of there's 1 hydrogen, but the other 3 groups are these T-butoxy groups, terbutyl oxides. So somebody might write it like this, or somebody might write lithium, aluminum hydride, O-terbutyl, with 3 of those. So tris, T-butoxy, lithium aluminum hydride. Now these are big, bulky groups. They donate some electrons back to the lithium and the aluminum, and they kind of tamp it down just a little bit, so it reduces to aldehydes, but does not keep going to carboxylic acids. So 2 reagents. First, turn it into a good leaving group with the chloride, with thionyl-chloride. Then this sort of LAH, but not quite as reactive. This lithium aluminum tris-T-butoxyhydride will stop at the aldehyde. That's one way. The other way is you can do a Fischer esterification, which we've seen in a previous video. I'll link here. And you can take an alcohol and some catalytic sulfuric acid, and you can make this an ester, which is a carbonyl oxygen carbon. And once you make an ester, you can reduce that. Instead of this compound, it's a different one called DIBAL-H. We won't get into what that is, but if you make an ester, you can reduce that with DIBAL-H. I'll just call that carbon, C double bond O, and it stops at the aldehyde. It reduces it and stops halfway. So those are the two ways of doing this part of the reduction with the red arrow. You can use thionyl followed by lithium aluminum hydride with 3 terp-butoxy groups on it. Or you could have done a Fischer esterification, alcohol and acid, followed by DIBAL-H. And those are how you go halfway from a carboxylic acid to an aldehyde. I hope that gives you a full understanding of oxidations and reductions. Subscribe to the channel, and I can help you more with your organic chemistry.